Hello, everyone. I'm Sixian Zhang, currently a PhD student at the Institute of Computing Technology of the Chinese Academy of Science. Here I'm very glad to present our work layout-based causal inference for object navigation. Previous works for ObjectNav task attempt to learn the association between the visual inputs and the goal during training. Such association is denoted as the experience. The experience performs a positive effect on helping the agent infer the likely location of the goal when the layout gap between the test environments and the prior knowledge is minor. However, when the layout gap is significant, the experience exerts a negative effect on navigation. To this end, we propose the layout-based soft total direct effect framework to adjust the prediction of the navigation policy. In particular, we propose to calculate the layout gap, which is defined as the KL divergence between the posterior and the prior distribution of the object layout. Then the STDE is proposed to appropriately control the effect of the experience based on the layout gap. Recently, the learning-based methods attempt to model the prior knowledge of the spatial relationships among the objects, so the agent could infer the likely locations of the goal based on the current observation. Such association represents the prior knowledge of navigating in training environments, which is denoted as the experience. To reveal the effect of learned experience, we propose to use the causal graph to analyze these navigation works. As shown in causal graph, the navigation model takes the observation and the goal as the input, and the predicted action is affected by the observation, goal, and the experience. Consider two cases of the layout gap between the navigating environment and the prior knowledge. 1. The layout gap is minor, and 2. The layout gap is significant. In the former case, the object layout is consistent in the current environment and the prior knowledge. Thus, the experience exerts a positive effect on the prediction of action. However, the effect of experience in the latter case could be negative. If the agent still relies on the negative experience to predict actions, it will suffer from poor generalization. Therefore, wisely utilizing the experience is essential. Motivated by wisely utilizing the learned experience, we propose the soft total direct effect framework based on the causal analysis. Our method can eliminate the prediction bias brought by the experience. To decouple the effect of experience, we construct the counterfact prediction bar A, representing the prediction is only affected by the experience while ignoring the observation and the goal. Then we propose the object layout estimator that calculates whether the effect of the experience is positive by measuring the layout gap between the current environment and the prior knowledge. Furthermore, our method will remove the counterfact prediction from the fact prediction when the layout gap is large to avoid the negative effects of experience. As for the object layout, we use the contextual relationship D to approximate the object layout. The D is composed of the context distribution theta I of k objects. Each dimension of theta I represents the probability that the object category Cj can be observed around the category Ci in an observation. We assume that the context distribution theta I follows the Dirichlet distribution, and the alpha I parameterizes the distribution. During navigation, the agent receives the visual observation at every timestamps. Based on prior distribution of object layout, the likelihood function of that this observation is observed can be calculated. Then, according to the Bayesian inference, the posterior distribution can be further calculated. The layout gap is determined by calculating the KL divergence between the posterior and prior distribution of object layouts, and serves as a weight to determine whether to remove the counterfact prediction from the original prediction in STDE analysis. This is the framework of our method. Our layout estimator computes the layout gap, and use it to alleviate the experience bias. The advantages of our method lies in the parameter-free and simple computation, and is easy to plug and play and boost existing methods. We evaluate our method in AI2 Thor, RoboThor, and habitat simulation. Firstly, we visualize the correlation between layout and success rate. The result indicates that the navigation performance on success rate during inference has a generally positive correlation with the layout similarity, which supports our motivation. Besides, our method can bring more obvious improvement in the categories with low layout similarity. We presume that the goals with a larger layout gap are more susceptible to the effects of the experience, thus benefiting more from our debiased method. The ablation study indicates the efficacy of each component in our method. The existing work can be benefit from our layout-based STDE. By incorporating our method, the performances of existing methods are improved. The trajectory visualization results indicate that the baseline agent is prone to get stuck in the locations where the target object usually appears in the training environments. The results demonstrate that the agent is easily influenced by the experience learned in training, which results in the failure of navigation. However, the agent, driven by our method, utilizes the learned experience more wisely, and tends to be more exploratory rather than suffering from the biased experience. Consequently, our agent achieves better performance and navigates with more efficient trajectories. Thanks for watching.